this lecture, I'll be discussing assignment problems, binary decisions, and their application. Assignment problems are a special type of linear programming models. Assignees are being asked to perform tasks, and assignees could be people, machines, plants, or time slots. So consider an emergency department. So we have 10 nurses and 10 rooms, and we want to assign each nurse to each room. So there are some requirements to fit assignment problem definition. The very first one is that the number of assignees in tasks are the same. So if we have 10 nurses, then we need to have 10 rooms. Each assignee is assigned to exactly one task. It means that each nurse is assigned to only one room. And each task is to be performed by exactly one assignee. If we assign one nurse to that room, other nurses cannot be assigned to the same room. Cost C sub ij is associated with each assignee I performing task j. So there is a cost for each assignment. The objective is to determine how n assignments should be made to minimize the total cost. One prototype example can be the job shop company problem, where we want to assign new machines to locations to minimize total cost of materials handling. Now here's the example that we are going to discuss and implement in Python. Machine Co has 4 machines and 4 jobs to be completed. Each machine must be assigned to complete one job, and the time required to set up each machine for completing each job is shown in this table. For example, for machine 1 and job 1, the setup time is 14 hours. For machine 1 and job 2, the setup time is 5 hours. Machine Co wants to minimize the total setup time needed to complete the 4 jobs. Determine which machine should be assigned to each job when we minimize the total setup time. Before we discuss the implementation details in Python, I would like to draw your attention to this network. On the left side, we see assignees, and on the right side, we see tasks. All assignees are fully connected to all tasks, and for each link, there is a cost. On the right-hand side, you can see the mathematical formulation. There is a cost function. The objective function is to minimize the summation of C sub ij times x sub ij. So let's look at our decision variables. Here, decision variables are binary. So if assignee I is going to perform task j, then the value is 1, otherwise it's 0. If you look at the set of constraints, we have 2 sets of constraints. The first one is defined for all assignees. The other one is defined for all tasks, because we want to make sure that each task is going to perform by only one assignee, and each assignee is only assigned to one task. So we see the summation over I and summation over j, then it's equal to 1. Okay, now let's try to implement this in Python for the Machine Co problem. In that table, we have 3 pieces of information. First, the list of jobs. So we have 4 jobs. The other list is machine. We have 4 machines, as you can see here. We use a list as the data structure because it's just a sequence of items. We also have a setup time or activity, which can be modeled using a dictionary. So we have a key and we have a value. Keys are pairs of machine and jobs. So machine 1 and job 1, the setup time is 14. The setup time for machine 1 and job 2 is 5 hours, and so on. So here we define 3 variables: job, machine, and activity. And that's all the input that we need for our linear programming model. Now let's define decision variables. To do that, we need to import GrowBPy. So from GrowBPy, import everything, all functions. Then we create an object named model, which is for our assignment problem. Decision variables, x sub ij are dictionaries. And here the decision variable, if you look at the formulation, has two indices, I and j. I refers to assignees, j refers to tasks. So we can define decision variables using a nested loop. For I in machine and for j in job, because we want to assign machines and jobs. Xij is equal to, we call model, then we add variable. Here we can say the v-type is binary. We need to specify the minimization or maximization types. So we call model dot model sense, which is a reservoir, equal to GrowB minimize. So this is a minimization problem. And then we need to update it. Model dot update. Let's run. Okay. So far we defined the decision variables and we are following the mathematical notation that we have here. X sub ij with two indices. I is defined over machine, j is defined over jobs, and x sub ij is our decision variable and its type is binary. Now we can define constraints. As you can see here, we have two types of constraints. One is defined for all i's, the other one is defined for all j's. And when we see summation, it means that we can use the quick sum function. So one for loop for I in machine. So we have one for loop for machine, one for loop for jobs. Model dot add constraint. Summation translate to quick sum. There is no coefficient, it's just xij. For j in job equal to 1. So when we use the quick sum function, we should specify which variable, which index. So it's the summation over variable j or job. And the outer loop is the for loop for machines, and it's equal to 1. The same for jobs. For j in job, we add another constraint. We have a summation, so we can use the quick sum. Xij, so it's the summation over I in machine and it should be equal to 1. Let's run it. There is an error. X. So we used capital X for defining the variable. So to see this error, we have machine 1, machine 1. So if you look at this constraint, so I have xi, comma I, while it should be xij, because that's how we define our decision variable. Now let's run it. Now we have the constraint for our model. So these two constraints make sure that one machine is assigned to each job, and each job is assigned to only one machine. Typical constraint for assignment problems. Now we can define objective function. For objective function, we see summation, so it translates to quick sum. So we can use quick sum, but we have two summations, so quick sum over both I and j, and we have a coefficient, and the coefficients are defined in variable activity, which is a dictionary. So activity I and j times the decision variable x, I and j for I in machine, also for j in job. So if you look at activity, these are the setup times for each pair of machine and jobs. So that coefficient times decision variables as our objective function. And this summation is defined over both I and j. When we are done with defining the objective function, we can assign it to our model. Model.set objective, then we pass this variable as an input. So we define the decision variables, constraints, and objective function. Now we can optimize the model. So we call model.optimize. So you can see the optimal solution, best objective value, but it's easier to print the result. Now we print outputs. First, we check the model status. If model.status is optimal, then print the result. Print optimal value is model.optval, which returns the value for our objective function. We also want to print the assignment. So that's the question we wanted to answer. Which job should be assigned to which machine? We define a for loop to go through the decision variables. Here, decision variables have two indices, I and j, so we will see a nested for loop for I in machine, for j in job, print I and j, and also their optimal value, xij dot small x. Now let's run this. Seems that there is a typo here. Okay, so the optimal value is 15, and here you can see the assignment. The first 4 rows are related to machine 1. So machine 1 is assigned to job 2, or job 2 is assigned to machine 1, and the value is 1. The value for other pairs is equal to 0. It means that just one job is assigned to this machine. The same for machine 2. As you can see here, job 4 is assigned to machine 4, and the value for other jobs equal to 0. And the same for machine 3. So job 3 is assigned to machine 3, and eventually for machine 4, there is just one non-zero variable, means that machine 4 is assigned to job 1. So that's how we can solve an assignment problem in Python using Groby. Now, I would like to discuss binary decisions and some of their applications. As you just saw, there are 2 possible integer values for binary decisions, 0 and 1. Example can be yes or no decisions. There are different applications for binary decision. One is investment analysis. The decision that we want to make is whether or not to invest a fixed amount. We use this type of decisions in capital budgeting decisions, upgrading a nation's defense force, and etc. So if we decide to invest, then the value is 1. If we don't make any investment, then it's 0. So it's a yes or no or 0-1 situation. The other application is for site selections. We want to answer this question. Should new facility be located at the potential site? If yes, then the value is 1. If no, then its value is 0. Binary decisions also used for dispatching shipments. Should a certain route be selected for one of the trucks? It can be applied to certain route, certain size of truck, certain time period for departure. So vehicle routing problems is one of the popular models under dispatching shipment category. We can also use binary decisions for scheduling interrelated activities. Should a certain activity begin in a certain time period? If yes, then it's 1, otherwise it's 0. Airline applications, also another interesting application for binary decisions. Here I have listed some decision types. For instance, we want to know should a certain type of aircraft be assigned to a certain flight leg, or should a certain sequence of flight legs be assigned to a crew, or if we want to know the reassignment of crews to flights to adjust to weather delays. So these are all interesting applications for binary decisions. In this lecture, I want to discuss a couple of applications. One is for site selection, the other one is related to investment portfolio. So consider this problem. The California Manufacturing Company is considering building new factory in Los Angeles or San Francisco or both. That's why we call it site selection problem. This company is also considering building one new warehouse. Choice of location restricted to city where the factory is being built. It means that if we want to build the factory in Los Angeles, then the warehouse should be located in Los Angeles. The objective is to find the feasible combination of alternatives that maximizes the net present value. It means that we need to have some input parameters to formulate the model. As you can see, the type of decision variables is binary. If decision J is yes, we assign 1, and if it's no, we assign 0. And we have 4 decisions to make. The first one, do we want to build factory in Los Angeles? The second decision, do we want to build factory in San Francisco? The third decision, building a warehouse in Los Angeles or building a warehouse in San Francisco. In this table, you can see net present value for each decision. $9 million for building a factory in Los Angeles, etc. You can also see capital required for each decision. $6 million for building factory in Los Angeles. And of course, we have some limits on available capital. So capital available for this company is $10 million. And the goal is to optimize total net present value of these choices. Net present value given by this function, 9 times x1. So from here in this column, you see the net present value for each option. So 9 times x1 plus 5 times x2 plus 6 times x3 plus 4 times x4 is the net present value, and it's our objective function. Now we can discuss model constraints. The first constraint is the capital required. So if we decide x1, so 6 times x1 plus 3 times x sub 2 through 2 times x sub 4 should be equal or less than this amount, $10 million. That's the money that is available. And that's what you see here. 6 times x1 plus 3 times x2 through 2 times x4 should be less than 10. Also, we only want to build one warehouse. So it means that we choose either x3 or x4. In order to model that, we can have x3 plus x4 less than or equal to 1. If x3 is 1, then this constraint makes sure that x4 is 0 because their summation should be less than 1. If x4 is 1, this constraint makes sure that x3 is 0 because their summation should be less than 1. Also, decisions 3 and 4 are contingent on decisions 1 and 2. It means that if we decide to choose the factory in Los Angeles, then x1 is 1, then x3 can be 0 or 1. But if we decide not to build any factory in Los Angeles, then x1 is 0, then this constraint makes sure that x3 is 0 because it cannot take on 1 because 1 is not less than 0. The same for the other decision variable, x4. So if x2 is 1, then x4 can be 0 or 1. But if it is 0, it has to be 0. Now you can see all constraints and the objective function in this slide. So we want to maximize the net present value. This is the objective function here. And we have listed all constraints. So on the right hand side, we just keep the numbers, everything else is on the left hand side. And xj is integer. If it is integer, then it means that the upper bound is 1, the lower bound is 0. Or you can just define that xj as binary. Now here's the practice for you. Try to write codes for solving this LP model. So look at this mathematical model. Define the list and dictionaries, the input parameters, and then define the objective function and set of constraints. And if you have any question, please connect with me during my online office hours or in one of our live sessions where we can discuss these problems. The other application for binary decisions is investment portfolio, and here you can see the problem statement. The board of directors of General Wheels Company is considering 6 large capital investments. These investments differ in the estimated long-run profit that they will generate, as well as in the amount of capital required, as shown by the following table, in units of millions of dollars. So we have 6 options. You can see the estimated profit and capital required for each option. The total amount of capital available for this investment is $100 million. So that's our constraint. Investment opportunities 1 and 2 are mutually exclusive. It means that if we choose to invest in option 1, then we cannot invest in option 2. And so are 3 and 4. So these two mutually exclusive, 3 and 4 are mutually exclusive too. Furthermore, neither 3 nor 4 can be undertaken unless one of the first 2 opportunities is undertaken. That's another constraint. There are no such restriction on investment opportunities 5 and 6. The objective is to select the combination of capital investments that will maximize the total estimated long-run profit. So we have a maximization problem, and it's the total estimated long-run profit. So again, decision variables are binary. If the decision is to invest in opportunity J, then its value is 1, it's 0 otherwise. P sub j denotes the estimated profit of opportunity J, and Cj is the capital required for opportunity, and you can find these numbers in this table. Now, let's discuss the constraints. So the first constraint ensures that option 1 and 2 are mutually exclusive. If I choose option 1, then x1 is equal to 1. Then x2 has to be 0. Now, if x2 is 1, then x1 has to be 0 because their summation should be equal or less than 1. The same for opportunities 3 and 4. Now, opportunity 3 can be undertaken if one of the opportunities 1 or 2 is undertaken, or both. So if x1 is 1, then x3 can be 0 or 1. But if both x1 and x2 are 0, then x3 has to be 0. The same for opportunity 4. It can be undertaken if one of options 1 and 2 are already undertaken. So if both are 1, let's say, then x4 can be 0 or 1. But if both of them are 0, then x4 has to be 0. And the decision variables are binary. Here's another practice for you. Try to write this code in Python and solve this LP model. And we can discuss it in our live sessions. In next lecture, I'll be discussing mixed integer